Hey everyone, welcome to your exam guide on ethers. This whole explainer is brought to you by Tutorial Haven. Now, this is a topic that, believe me, shows up all the time on exams. So today, we're going to absolutely master the three things you have to know: how to spot them, how to name them, and the one key reaction you just can't forget. Let's dive right in.
So, first things first. Before we can do anything else, we got to be able to identify an ether in a lineup, right? What is the one key feature that just screams, hey, I'm an ether? And here it is. This is your answer. Every single ether, no exceptions, is built around this core structure. You've got an oxygen atom that's acting like a bridge between two carbon-based groups. This ROR linkage, that's the one visual cue you need to hunt for on your exam. If you see that oxygen bridge, you've found your ether. Simple as that. And you know what? That oxygen bridge we just talked about, it explains pretty much all of an ether's key properties. See, unlike alcohols, there's no hydrogen attached to that oxygen. And that one little difference means they can't form those strong hydrogen bonds. And that's why they have lower boiling points and don't really dissolve in water. For your exam, just remember these two things. They are chemically super stable, which makes them awesome solvents, but, and this is a big but, they are also highly flammable. Okay, so we can spot them. Awesome. Now for the part of the exam where you can scoop up some really easy points: naming them. If you can get this system down, I guarantee you're going to get these questions right. So you're going to see two naming systems. The common names over on the left, they're pretty simple. Just name the two side groups and tack on the word ether. Easy. But for your exam, you need to be an expert in the formal IUPAC system on the right. This is like the official language of chemistry. The key idea here is that we treat the smaller side of the ether as a branch, or a substituent, and we call it an alkoxy group. So diethyl ether becomes ethoxyethane under IUPAC rules. Let's break down exactly how that works. Here are 4 simple, repeatable steps you can use every single time. 1. Find the longest carbon chain. That's your base name, your foundation. 2. The shorter chain and the oxygen, that becomes the oxy prefix. 3. Number the long chain so that the alkoxy group gets the lowest possible number. And 4. Just name any other substituents like you normally would. You follow these 4 steps and you just can't go wrong. All right, let's put those steps into action. Take a look at this molecule. What's the longest chain? Well, it's 3 carbons, so our base name is propane. The other side is a 1-carbon methyl group with the oxygen, so our prefix is methoxy. Now, where's it attached? To carbon number 1. You put it all together, and what do you get? 1-methoxypropane. See? It's a really simple logical system once you get the hang of it. Okay, let's try another one. What's our longest chain here? 4 carbons, right? So it's a butane. The shorter side is a 3-carbon propoxy group. Now, here's the key question. Do we number from the left or the right? Well, we number to give that propoxy group the lowest possible number, which in this case is 2. So the full name is 2-propoxybutane. Once you master this logic, you are all set. All right, naming is sorted. Now, how do we actually make these things? For your exam, you really don't need to know every single method out there, but there is one gold standard reaction that you absolutely, positively have to know. If you only have brain space to remember one synthesis method, make it this one. Textbooks and examiners, they just love the Williamson ether synthesis. It's considered the most versatile and important way to make ethers. This is your #1 must-know reaction for this entire topic. So here's the play-by-play. It works in 2 steps. First, you take an alcohol and you add a strong base. The base just rips the hydrogen right off the oxygen, creating this negatively charged and super reactive alkoxide ion. Then, this powerful alkoxide ion goes on the attack. It acts as a nucleophile, attacking a primary alkyl halide and kicking out the halogen. And the result? A perfect ROR ether bridge is formed. So, we can identify them, we can name them, and we can make them. But how do they react? And are there any special cases you need to know about to really get those top marks? Let's find out. This brings us to their single most important chemical property. Remember how alcohols have that reactive OH group? Well, ethers don't. That oxygen bridge is locked in place and it doesn't have an acidic hydrogen to give away. This makes them incredibly stable, or inert. And that, right there, is their superpower. They're fantastic solvents precisely because they won't mess with whatever reaction you're trying to run. Now for the special case. This is the kind of thing that separates the good students from the great ones. These cool-looking things are called crown ethers. As you can see, they're these big cyclic ethers,
and they tend to show up in the tougher exam questions because they can do something really unique. So their naming, it's actually pretty logical. It follows this X crown Y format. X is the total number of atoms in the whole ring, and Y is just the number of oxygen atoms. So in this example, 18 crown 6, you've got an 18-atom ring, and 6 of those are oxygens. So what's their superpower? Well, the oxygen atoms point inwards, creating this electronegative cavity that is perfectly sized to trap positive ions, or cations. It's kind of like a molecular cage. Okay, wow, we have covered a lot. So let's boil it all down to a final rapid-fire exam cheat sheet. If you only have a minute to review, these are the 3 points you absolutely must remember.
Number 1, naming. Just focus on that IUPAC rule. The longest chain is your base name. The shorter chain plus the oxygen is your alkoxy prefix. That's it. Got it?
Number 2, synthesis. The Williamson synthesis is your go-to. The formula is simple. An alkoxide attacks an alkyl halide. That's the reaction you have to know inside and out. And finally, number 3, reactivity. Ethers are stable, unreactive bridges. And why? Because unlike alcohols, they are missing that reactive OH group. That one single fact explains why they make such great solvents. And that leaves us with a final thought to chew on. We saw how those crown ethers can trap ions like sodium and potassium. So where in biology, where those exact ions are absolutely crucial for things like, say, nerve impulses, where might that ability be a total game changer? It's a pretty fascinating link between simple chemistry and complex life. That's your deep dive into ethers. I hope this exam guide from Tutorial Haven helps you completely ace your test. Keep learning, and we'll see you next time.